and a lot of what I've been talking about is the engineering that goes alongside the preparation of mine waste, and in particular mine tailings, and in so much as, you know, how do we dewater that material, how do we transport that material, can we put that material underground as mine backfill. So building on a lot of the what you've heard so far is what we're trying to achieve, and hopefully what Chris and I will now talk about in the second half is how we actually achieve that. So some of the overriding principles that we're trying to meet. I'll try and give you examples of engineering solutions. They're not, this is not a comprehensive list. Obviously you will appreciate that there are many different technologies out there, and in the time I've got, I'm not going to be able to go through all of those, but I want to give you a flavour of some of the things that we can do to meet those objectives and those principles. And I'll try and fill that in with some case examples, just to give you some of my experience and anecdotes of where things may or may not have worked. I'm going to have to work off two different media here, so if I get myself confused, then I'll have to apologise now for it. So, two overarching questions. Again, trying to connect back to what you heard this morning. How do we minimise what we're doing? So, how do we reduce the problem in the first place? We have a saying in English, I imagine there's probably a similar one, is prevention is better than cure. So if we can avoid the problem in the first place, it's better to do that and then try and find a solution to solve it afterwards. But if we are going to have an impact, how do we actually minimise that impact? So you can consider my presentation in two parts. So the first part will look at what we might do to minimise that impact, minimise the production in the first place, and then secondly, how we go about minimising its impact. So, as I say, prevention is better than cure. So we want to mine more of what we want and less of what we don't want. Okay, so in the green box here, you can see that if we can improve our resource definition and we can be more selective in our mining methods, then we can get out more of what we want and less of what we don't want. So we don't have to take out the material that's not necessary, so we're mining less. But set against that, you can see that we're faced across the globe with reducing resource grade, and that's pushing us to be less selective. So we're increasingly seeing larger and larger operations which are chasing economies of scale, so they're actually mining less selectively. So the two things don't really sit in balance. But there are some things we can do to try and improve that. So we can look at how we improve our head grade going into the actual process plant. And I'll come on to a few examples of that in a minute. And then once we've got that material into the process plant, how do we actually go about getting the most out of it? So that again, we're minimising the amount of waste and the amount of tailings that we're producing. So those are sort of some overarching principles that I think are important in addressing some of those core issues raised this morning. So head grade improvement, again, what we're trying to do is we're trying to minimise the amount of material we bring to the process plant in the first place and the amount of material that we have to crush and grind. From a geochemistry perspective, the larger the surface area, the bigger the problem we're going to face. So if we can actually avoid breaking that material down before we start, then we're minimising the impact we're going to have later on. Also, pre-concentration of that material, it means that we can actually run a larger mine through a smaller process plant. So again, that harks back to the opportunities that we see in terms of running bigger deposits with higher production rates to achieve economies of scale, but still meeting that requirement to only treat what we want to treat. So if we can separate out the waste material before it even reaches the process plant, maybe there are other things we can do with it. There's a lot of examples of operations producing clean byproducts, because often the waste material is it's an inert material. From a simple mining engineer's perspective, it's an inert material versus perhaps the inert or active material, the ore that you're trying to mine. If we can separate out that inert material before it even reaches the process plant, that may be a saleable product we can produce somewhere else, or it can be treated in a much more benign way. The moment we throw all of it into a process plant and then treat it all as one product, we've suddenly increased the impact we're having because we've dispersed, if you like, the nasty, the inert material amongst the inert material, and we're now treating a much larger volume of material with active or inert conditions. Okay. So in terms of pre-concentration, there's a variety of options we can look at, and I've pulled out three that I think are starting to come online and start to see more of it. So the first one is ore sorting, and this uses physical variations or differences between minerals, be that optical, magnetic, X-rays, to actually separate out mineral that we want and waste that we don't want. We've worked last year, or the last couple of years, I've worked on a project in Europe where we've the operation has sought to utilise ore sorting to minimise the amount of material going to the process plant, and by doing that they're able to run a 500,000 tonne a year mine, but they're only sending half that material to the process plant, which means that they're only generating half the tailings equivalent to the ore they're mining and the volume they're producing, which has actually allowed us to put all of the tailings back underground. So immediately we've got a situation where we've, in a sense, from a tailings perspective, had a zero impact on surface, because we've actually overcome that swell factor that we naturally see with minerals when we process them. Normally if we take out 100%, we treat 100%, we can only get 50 to 60% of that material back underground. In this scenario, we got it all back underground because we were able to isolate only what we wanted to treat. The waste material that was the reject from the sorters was actually a marble, and that was taken away, and that can be sold separately. So it's actually identifying what we want and what we don't want. Another option is coarse particle flotation. So this is a developing technology. It's come out about from flash flotation, and there's some now fluidized bed technology which is helping to improve that. But here what we're saying is that we might need to crush the material, but let's not crush it to its ultimate size fraction. Let's crush it to, let's say, 1 to 2 millimeters, and do a float at that stage, so we can isolate the more of the mineral that we want. And again, it's about putting what we want through the process plant. This is a particularly interesting technology because we can actually do this underground. So actually what we can do is we can separate out a coarse flotation waste underground, which can actually be placed back into the voids underground, never needs to come to surface. And that's what there's a number of companies looking at that technology. So we're only bringing to surface what it is that we actually want. And then finally, this one's been around a lot longer, but heavy media separation. Again, using the density difference between waste and ore to actually isolate what we want. Again, I think that's a more known technology, but again, you'll start to see it not purely from a processing perspective once everything's in the process plant, but as a pre-concentration. So how do we isolate those ore streams or those material streams before they get into the process plant? The next aspect is getting more from ore. It's a common phrase I've seen a number of different companies use, but once we've got it in the process plant, how do we maximise what we want from it? We've all seen stories of people going over old tailings dumps because there's mineral left in there. Well, how do we go about making sure we get that first time round? So, and that gives us the ability that for the same number of tonnes through the front door of the process plant, we're actually putting less in the tailings dam, and we're actually recovering more value from what we're doing, which we should all be interested in that from an operations perspective. Again, there's a really wide, next slide up, there's a really wide variety of different technologies out there. A few that I've struck on again for the purpose of giving you some illustration. Particle liberation. There's been a lot of work recently, or in recent years, looking at how we actually break particles. So traditionally we crush it, we grind it, and it goes through a float circuit or a CIL circuit. If we can actually be smarter about the fracture mode that we're looking at when we're actually breaking particles, we can actually improve the liberation of the particles. So a good example is high pressure grinding mills, where we're looking at breaking particles along natural fracture planes, which increase areas of particle of the ore surface that we're looking for, which improves our ore recovery. And it also means that we're not necessarily having to crush and grind it as fine to achieve the same liberation and therefore the same recoveries. Where we do have to grind it, the opportunities associated with selective ultra-fine grinding are of benefit. So we're starting to see grind sizes go down into the tens of microns as targets. But that, as I'll talk about later, is counter to trying to engineer our waste products, because the finer it is, the harder it is to treat the far end. So rather than throwing everything through a regrind circuit, we've got to get smart about what we put through there. So we're looking at cleaner circuits, improvements in cleaner circuits, so that we're only regrinding the very fine end of the product, just trying to extract that last 5 to 10%, but the bulk of it we've already got, so we're not grinding everything to 20 microns. Control and automation is another area that I think needs a lot more focus and attention. It's a common thing, but equally there are examples, and dare I say it, I've worked in examples where we didn't have a single piece of automation in the entire process plant. And there you rapidly lose efficiencies. But more than that, we're starting to see predictive automation. Historically, process plants have always been reactive. So we measure the result and then we adapt what we're doing in the process plant to address that, and so it's always reactive. We're starting to look now at proactive management of processing. And that even comes from, there are technologies out there where people are tracking, based on the geological model, where each shovel load comes from in a pit or underground, and they're tracking that through into stockpiles ahead of the process plant, so that they have a predictive forecast of the mineralogy coming through the process plant at that moment, and adapting the process conditions in advance based on that forecast. And that's allowing us to be more efficient and effective in recovering what we want from the product, and again, reducing the amount of material that goes out the back door to the tailings dam. And then finally, there's a growing development of secondary recovery strategies. So one of the interesting things is you go into an operating process facility and you start talking about secondary recovery. Sometimes you meet a bit of resistance, because obviously there's an expectation that people are they're already recovering everything they can. But we can actually do a lot of things. Once we've had our first crack at recovering our gold or copper or lead or zinc, we can actually go around again and have another go at that. And there's things such as fines agglomeration, so that we actually recombine some of those fines, put them in a stockpile and heat leach them. Now you can't heat leach a tailings dam because the fines particle is too fine and you don't get the percolation rates. If we can agglomerate that material, then actually we can suddenly start taking a technology which is designed for low-grade materials, and we can apply that to our secondary product recovery. And then finally, I hit on the scenario where there's examples in South Africa of tailings dams being reprocessed. I think they're up to about their 4th time now. So they've gone over them 2 or 3 times for gold recovery, and they're now going over those same dumps for uranium recovery around in the South Africa and the Johannesburg gold belt. Why do we have to put it in the tailings dam first before we go and try and recover that material? There's a lot of opportunities working with third-party companies who perhaps have different cost structures to the main producing company, who will take tailings, or your tailings, and they'll retreat those before it then goes to the tailings facility. So we're actually having another bite of that cherry before we've actually, before it goes to the tailings facility, to try and maximise what we're getting out of there. And some examples include pyrite recovery for sulfuric acid production, chrome recovery from PGMs, platinum group metals, heavy mineral extraction from oil sands. That's an area that there's a lot of work being done on. Obviously the oil sands, they have a significant tailings management challenge, so anything they can do to reduce the amount of material going there is of benefit. Coal fines recovery, and then rare earths. There's a lot of work going on, a lot of research into multi-gravity separators to try and recover rare earths. An example is in the UK there's a new tungsten operation, and there's a lot of work being done at the moment there to take their tailings before it gets to the tailings dam and retreat that as a third-party operation, so it's not the main operator, to try and recover rare earths from that material, and then pass it back to the main operator to put back in their tailings facility. But again, what I'm trying to hit on is, rather than let it go into the tailings dam and then try and retreat it, let's try and be smart about it and recover that first. Okay, so those were some ideas, just examples, I guess, on how we can look at trying to minimize the amount of tailings, amount of mine waste that we're producing. So if we accept that we do have to produce mine waste, what do we do to try and minimize the impact of that? So I've broken this into 3 areas. So the first is, how can we engineer our waste? How can we be smarter about what we produce so it's easier to manage, it's more cost effective to manage, it has less impact once it's there. The next one is minimizing surface disturbance or impact. So if we've got to put it on surface, what do we do with it that makes it least harmful, the least impact? And then finally, how do we reduce the risk? Now I know Chris is going to talk about all of this as well. I'm not going to dwell on it too much in terms of the geotechnical risk. What I'm going to focus on is some of the engineering, the processing of tailings and mine waste prior to it going in the tailings dam. So we're looking at tailings, dewatering, that sort of thing. Okay, so engineering of our waste. Let's try and consider waste as a product, not something that's left over after we've done everything else we want, because that's typically what it is now. As someone who works with tailings and mine backfill systems, we have the unonerous task of the fact that no one really cares what they give us. It's whatever they've got left, and that's what it is, and there's no control over it. No one actually measures the particle size of the tailings on a regular basis to make sure it's within the specification. But actually, particle size or mineralogy can have a huge impact on what we do and how we manage it. So if we think about dry stack tailings, which has been mentioned already, the cost difference you can achieve by having a coarser tailings versus a very fine tailings, if you're trying to filter that material, is absolutely staggering. Okay, we're talking tens of millions of dollars. By the fact that perhaps you could offset some of your recovery, a small component of your recovery, in lieu of trying to produce a more manageable tailings product. So we need to start doing cost-benefit analysis of what's more valuable, the cost of disposal of our tailings or the small amount of additional recovery we might get. And I appreciate that. I'm talking, if you like, from both sides of the fence. On one side I'm trying to say that we should recover everything we can, and on the other side I'm saying perhaps we need to be more selective about what we recover so we produce a waste that's more manageable. And it is a balance, and it is a challenge, but we have to think about it more, to coin a horrible phrase, holistically, more rounded. We need to think about the whole process, not just one particular component, and break down silos within our organisations to actually look at different aspects of that. An example of where people are trying to engineer waste, there's a cooperation between Goldcorp and FL Schmidt. I think they've patented or trademarked the name EcoTails, and this is a drive to try and co-dispose coarse waste rock and tailings in one product by producing a fast filtering tailings, so trying to minimise the filtration cost, and then try to, on a large scale, manage the co-mingling of those two streams. I think at this stage it's still very much a prototype, and they're looking at putting in, I believe at Eleanor in Canada, they're looking at the first large scale trial, which is somewhere in the order of about 300 tonnes an hour. But it's an example of where we're trying to be smart about our waste management and actually try and look at it in advance and try not to just do it as deal with whatever's left. They're trying to be proactive about it. So, okay, we know that we're gonna actually dispose this material. How do we minimise the impact it has once it's there? I like I've heard a phrase, and I talked about it last year, I think, at the MINEX seminar that I attended in Serbia, which is talking about a void resource. We're all very familiar with mineral resources, but what about void resources? When you hear that the best available technology says that you must consider disposal in underground or in pits and things like that as a precursor to disposal anywhere else, and demonstrate that you've been able to do that, or that you can't do it. We need to start thinking about what those void resources are, where they sit within our operations, and how we can actually utilise those. Another case example, working with a company in iron ore mine, they have an opportunity for an underground operation and an open pit operation, and what we're trying to get them to look at is how they schedule those. So they've got a current deposit or a tailings facility they can use. Currently they're looking at doing the underground and the open pit. We're trying to get them to look at that again and say, okay, if you do the open pit first, you're then developing a void resource so that the waste you produce from underground can then go into that pit. So it's just a sequencing thing, but if they do it the other way around, it's all got to go in your surface tailings facility. And so they're not making best use of the void resource that they're going to create. And here's a challenging thought: whether we actually can we make an argument to actually create void underground, for example, if we can, in scenarios where we've got a large mass pool of concentrate, or we can isolate perhaps a high sulfide waste from the tailings, is there an argument that says if we produce a void underground, we're doing it for the benefit of putting the waste into it, rather than actually mining the resource? So the primary driver is a void resource, not a mineral resource. I don't know if I've made that particularly clear, but there could be scenarios where you can justify taking low grade because you get a cost benefit by being able to put some of your waste back into that void. I suppose that's what I'm trying to say. And then, again, on the theme of minimising surface impact, how do we look at progressive closure and rehabilitation? If we have a vast, wet, flooded tailings facility, there's very little opportunity for progressive closure in that scenario. It's there until you close the mine, and then you've got your closure liability. If we're looking at new technologies, be that filtered tailings, paste tailings, does that give us the opportunity to actually develop systems where we can progressively close them as we go? So actually what we're doing is we're moving some of that long-term liability, closure cost, into our operating cost and paying for it as we go. So again, trying to think around it rather than, I guess, take a generic traditional view. Okay, a couple of slides, an example on in-pit disposal. It is increasingly becoming a driver to actually utilise those old abandoned voids, abandoned pits for tailings disposal. And I guess there is an argument to say that the more holes we make, the more opportunities there is to put material back into them. It's also often seen as a beneficial function from the perspective of local stakeholders. You're actually closing out what is otherwise going to be an impact on the surface, or a scar on the surface. We can close that out, we can rehabilitate it and return it broadly to what it was before it started. And deposition into those facilities can include waste rock, it can include slurry tailings, filter tailings, thickened tailings. We can do a manner of different things in there. But again, it's being able to identify those resources and then engineer solutions to actually put the material into them. I pulled out a couple of considerations because it's not just simply a case of poke the pipe into the pit and open the tap and assume it's all going to be fine. We've got to think about some key aspects. I mean, geochemistry is one of the most important ones there, especially as we get that rebound and we actually start to flood that pit with groundwater. What does that do from a geochemistry, from a leachate perspective? So we need to be able to demonstrate that what while it may be solving a problem on one hand, we're not creating a problem on the other. As a way of trying to illustrate some of those considerations, I've borrowed, it's a case study that was presented at the Minefield conference, ironically, last year. And the reason it was presented at Minefield was the case study talked about how an operation, in this case Pinos Altos in Mexico, was able to use the fact that it had to have a filtration system because it had to have mine backfill, and use that to springboard itself into a open pit for surface disposal. So it was trying to co-support each operation, because on their own, I don't think each one justified itself commercially, but by the time they were able to justify that they could do backfill with the filters and they could do surface disposal with the filters, suddenly the cost-benefit trade-offs proved to be successful. So I need to acknowledge the author, Ibrahim Karadzic, and if anybody wants a copy of this paper, I can provide you a full reference for it. But one of the key things that that they had to manage with this, looking at the geochemistry, was how do they manage the infiltration water, and also they had a large fault structure down one of the walls of the pit, which had a high inflow rate, and so they had a leachate issue, or potential leachate issue. So just some of the things that they introduced in this scenario, there was a significant basal drainage layer that went in, so that they could actually recover the water from the base of that pit as the operation progressed. So any leachate water that did migrate into that area, they were able to actually recover that and treat that. So they had it was a long-term operational closure, I guess, mechanism, but it was something that they had to do. But again, it demonstrates that it's not just a put it in the pit, forget about it. This was quite an engineered system at the base of the pit. The next thing they needed to do was try to isolate this high water bearing feature in the wall, in one of the walls. So what they did there, which was quite neat, was they actually used the paste backfill system that they had. They produced a cemented paste backfill which had a very low permeability, and they actually placed that, and you can just see it. There you go. So put the slide on. I'm sorry. There we go. So you can just see that here. This is actually effectively a barrier layer of paste fill that they progressively, as the fill inside the facility, as the fill increased inside the facility, they brought this barrier layer of paste fill up the side with it. So what they were doing was effectively putting a low permeability barrier against that wall. And then with inside that, so on the right hand side here, they then used the filter cake from the filters, again at the backfill plant, or the filter plant, because it had a dual purpose, to actually place the material within that void resource. And again, what I'm trying to demonstrate here is that there are opportunities to utilize infrastructure that we might have for one purpose to actually springboard into another purpose. And that's been a very successful solution. Next aspect to talk about is mine backfill. This is something that's close to my heart and what I spend a lot of my time doing. But again, it has a dual purpose. I mean, we often look at mine backfill from the purpose of increasing our mineral resource, because it allows us to mine more material underground. But from an environmental, from a waste management, and from a sustainability perspective, it gives us the opportunity to put a lot of that waste material back underground. Now, the natural swell factors we see typically restrict us to only getting about 60% of what we mine back underground if we're processing all of the ore that's extracted. If we can go down that pre-concentration route that I spoke of at the beginning, we can actually start to move that balance. And we are looking at scenarios where we're putting all that material, all the tailings, back underground, and thereby eliminating the need for a tailings dam, which often is one of the most challenging aspects of any environmental permit to obtain. From a perspective of surface tailings management, we need to think about particle size. And I've put an example here of just where we might have a mill tailings, so this might be a whole plant tailings, the blue line, and then the red line might be something that we use as a hydraulic fill. Now the difference, without getting too much into mine backfill technology, but with a hydraulic fill we're only taking a coarse fraction because we want a fast filtering or a fast dewatering material underground. That has the complication that we're then producing a very fine material that we still have to store on surface. So we're not necessarily addressing all of our problems. We're solving one but creating another one. So paste backfill, hydraulic fill, they have different benefits. Both do let us put material back underground, so therefore we're putting less on surface. And we also have the opportunity to be selective about what we put underground. We're working on a project right now with colleagues at SRK where we're looking at isolating the high sulfide material and blending that with some of the low sulfide material that's produced from the process plant and ensuring that all that high sulfide material is going back underground where we're binding it up with cement, reducing its mobilization potential and effectively sterilizing what would otherwise be the most higher risk or higher contaminant potential material we're storing in a more controlled way underground, so that the bulk of the surface disposal is the low sulfide, less onerous material. So backfill gives us that opportunity. Another aspect is that often, especially nowadays, we're looking at, there's a lot of momentum to restart old mines, to look at re-establishing operations which have previously existed, and so there's abandoned mines underground. So again, there's a void resource that we can utilise there, and mine backfill allows us the opportunity to do that. We have another operation in the UK which is looking to restart, where there's been 350 years of tin mining, and we have the opportunity to, again, not have a tailings dam when we restart an operation, because we can actually put all the tailings back into those old voids, using mine backfill technology to minimise that surface impact. A couple of other less tangible things. If we're using mine backfill, we should be able to be more selective in our mining underground, so we're going to get a less diluted product from underground. So again, we're mining more of what we want, less of what we don't want. We're leaving the material we don't want underground where it's happy. And then finally, we're faced with a project where there's a need for water treatment, water from an old pit. As part of so the operation is looking at disposing of the bulk of its tailings in an old pit, but that pit is currently flooded. So they're treating the water from that pit, producing a filter cake, precipitate. We're then taking that precipitate, mixing that with some of the tailings and placing that back underground where we're sterilising it and controlling it. Because otherwise that's a very hazardous material that they're producing as the water treatment plant sludge. And so we're, again, co-disposing of that underground in a place where we're controlling it, allowing another void resource on surface to be used for the tailings. Because that operation, for a number of reasons, won't be permitted to have a tailings facility or a traditional tailings facility. Okay, reducing risk. So this is the final section that I'm coming on to. And what I'm doing is I don't want to talk about the geotechnical aspects of tailings disposal, because I'm going to leave that for Chris. What I want to talk about is how do we dewater tailings? So how do we get the water out? I'll be talking later in the week about tailings dewatering and about tailings management, and the fact that one of the biggest aspects we face, or challenges we face, is that we store too much water with our tailings traditionally. And actually, when we look at what motivates the failure, it may not be the water in the tailings facility that causes the failure, but what exacerbates the impact of that failure is the volume of water we're storing. So we're storing huge amounts of water, which, if we do have a dam failure, that's motivating all that material to come out. So how do we minimise the amount of water? How do we get the water out of the tailings so that we're storing it in a lower risk condition? And I'm going to talk about two aspects. One is thickening and one is filtering. Neither are new, but I'll give you my perspective on those and where I think they're going to go. So tailings thickening. Okay. It's not new. Okay. Patented first by John Doerr over 100 years ago. Okay. And what we're ostensibly using is gravity. familiar with some of these terminologies: conventional, high rate, high density, paste, and then there are actually other rateless units out there which can have application. Ostensibly, this is a sort of a simplistic view, but as you get thicker, the size and shape of those thickness changes. So we can go conventional, where this is a very traditional unit, potentially no flocculation, potentially no feed wells, and so very little optimization of that. We're just providing a large area which is still and allows material, the solids, to settle down with the water overflowing at the top. Moving on, we look at high rate thickening, where we're introducing flocculant. We're putting feed wells in the centre to actually engineer the mixing of the flocculants with the particles to improve the settling rates, to sensibly coagulate or flocculate those particles so they settle faster, and we can reduce the size of it. So, as an example, I think, Chris, with you, I worked on a project where we looked at an operation which was operating 13, 50 metre diameter conventional thickeners, and we were able to replace all those units with a single 100 metre high rate unit, just purely because of the optimization of the flocculation in the feed well. So we can be smarter about it. We then start moving over to the higher density and the paste thickening ends, where we're starting to build up the sidewall heights you can see here. So in addition to just purely gravity settlement, we're now starting to see consolidation helping to improve the underflow density and push more of the water out. And so you can see that follows this sort of transition of getting thicker. And there's also a progression of time. So this is where we started, and this to an extent is where we are now, although there is still an application for high rate thickening. I'm not an advocate of everything must be paste thickening. I'll talk about an example of that in a minute. Key aspects of thickening is gravity induced. There's nothing we can do about that. Gravity is usually pretty constant, but we can use flocculants to aid settlement, so we can coagulate those materials, help them settle better, as I've said. The settlement, the other aspect we can influence is the material we're putting in the beginning. So particle size is important, mineralogy is important, water chemistry is important. We can actually control all of those things, and again, go back to what I was talking about in terms of engineering of our wastes. If we actually start looking at this seriously, we can start playing with these in our process to actually optimize how this performs. And that drives cost savings, which at the moment is the biggest inhibitor to people doing the best thing they can for tailings management, is cost. We'd all love to do the best possible aspects for tailings management, but tailings is a cost. It always has been, it always will be. But if we can actually be smarter, we can actually try and optimize that. And then we can actually we can control and optimize some of the underflow densities as well. So we can control the flocculant dosing. I talked earlier about how we can preemptively forecast mineralogy coming into process plants. There's technology out there now which is proactively using that forecast of mineralogy and proactively addressing or adapting the flocculant dosing so that we optimize the product. If you think about some of these big thickeners which might have residence times of up to 12 to 24 hours, there's no point reacting after the material comes out the bottom and you've seen the density of it to then change the flocculant, because that ship passed 12 hours ago. So if we can actually do it in advance and proactively, we can actually we can drive the performance of these units up. Okay. A slide on paste tailings. If we go back about 10 years, I would say, it was the panacea. Paste tailings was the best thing since sliced bread. Everybody was going to do paste tailings. It was going to solve all of our problems. You agree, Chris?
Yes.
Yeah. And I was one of those people. I would put my hand up to that. I thought that this was going to be the best thing ever. It is and it isn't. It does give us the opportunity to vastly reduce the amount of water we store in a tailings facility, but it is not applicable to everything. It is not a fix-all solution. It's important that we actually understand what a paste is, because there's a lot of talk about what pastes are, and you can put half a dozen paste engineers in a room, and none of them will actually agree. Some of the definitions that I've used or I've seen, and I think it's important to understand what you're trying to achieve when you're defining what a paste is. So one is a non-segregating material. Another can be a material with a yield stress or rheology passing 50 pascals. Something with a measurable slump is another one, and there are a vast array of different ones. But again, as I say, I think it's important that we focus on what it is that we're trying to achieve when we're starting to try and define these things. And some of the considerations that go into whether or not paste tailings, and from a perspective I'm thinking sub-aerial deposition, so not underwater, where we're creating beaches above the water exposed to the air. So climate, they're good for they're good in dry or arid climates, where we get the benefit, we get the cost benefit of the water recovery, because that helps to offset some of the operating costs to actually put that material out there and to thicken it. Sub-aerial disposal, is it suitable for ARD type materials, so high sulfide materials? To give you an example where I think that it's been demonstrated it is, it's not always the case. And I'm looking at you, Carl, because from a geochemistry perspective, exposing high sulfide materials to the air, not always a cool thing to do. Tends to be orange, but I have some examples where it's not. Footprint. It does, I mean, we've all seen, or a lot of us perhaps have seen the examples in Australia where there is no extensive footprint restriction. So we can produce these fabulous circular deposits, and we can deposit these wonderful cones in the middle which benefit from excellent rotation of the deposition, so we can get really good layer drying. But that's not always the case. So we can't always focus on that. If we're in valley dams which are quite restrictive, it doesn't always work, because we're not actually getting the desiccation of those layers to give us the shear strength to actually achieve what often is the target, which is positive stacking angles, to improve our deposition factors. It's important to recognise that if you are going to go down a paste tailings route or a high thickened tailings route, water management becomes more acute. If we look at large water bodies, large traditional wet tailings dams, we have huge attenuation periods in those water dams. So we have the opportunity to absorb some of those process fluctuations that we see day by day in that attenuation period. If you're immediately getting your water back 6 hours after it left the process plant, you're much more sensitive to changes in the water chemistry and that impact that subsequently has coming back around to your process plant. So your water management does become an issue. And it does require higher levels of management. Technically, people have to be smarter about it. You have a higher expectation of your tailings operators. It's not a case of it just goes down the end of the pipe and you forget about it. It is actively managed, and there's a lot more control and process that goes into it, so people shouldn't go into it blindly. I talked about this example, I haven't got a slide on it, about where people, there's a operation in Europe, it's a high sulfide operation, it's mining in the Iberian pyrite belt, high pyrite levels. I was involved in a project where we took that from a sub-aqueous system into a sub-aerial system using paste technology. The key driver for why it worked was that we had a non-segregating material. The fact that it didn't segregate when we placed it on surface meant that we reduced the infiltration rate of oxygen into that material, because there was a good mesh of large and fine particles. And what that's done is, because we get a low air infiltration rate, we don't see the oxidation rates. And that operation is successfully depositing very high pyrite material on surface in the air because of the paste tailings condition. So it can be done, but again, it needs management. And they have significant water management issues. When it rains, the top layer of the top surface has oxidized to a degree. So when it rains, they get a very low pH flush off the surface of that facility. So they have to manage that. So again, it's not a slam dunk, let's say, but it does provide them the opportunity. And from their perspective, that operation, it avoided the need to expand their tailings facility. They could go up vertically rather than out, which from a footprint perspective addressed their motivation. So it can be done. Where's thickening going to go in the future? There's a lot of talk about filtered tailings, about it being, that's what we must do, and ultimately it is the best answer in most scenarios. But there is a vast difference in cost, and we can't ignore the cost between a thickening system and a filtration system is sometimes orders of magnitude of cost difference. And so thickening is always here to stay. So what can we do to actually improve how we thicken and what we can do with thickened tailings, or tailings in general, using thickeners? So one of the key things from my perspective as an engineer working with tailings day in, day out, is how do we improve the confidence of thickening? I have a client which has a number of paste thickeners which can achieve on them a particular material solids underflow densities up to 70% solids. They won't go past 50% solids because once upon a time someone bogged the thickener. They caused the thickener to clog and it blocked, and they had to shut the whole operation down. And unfortunately, the first reaction was that they asked that person to leave the business. That now means that nobody will even challenge the thickeners to work where they're supposed to work because they don't have the confidence. And why would they? I mean, it's their job on the line. They don't care. So we have to improve the confidence that we see with thickening, and that comes from things such as improved feed bed systems, feed bed dilution systems, designing thickening operating windows. The number of systems I've seen where thickeners are designed for one particular feed stream. It's at this solids density, it's this mineralogy, and it's this flocculation dose. Well, that's nice because that's what you did in the laboratory, but actually the mill, as I've said before, they don't really care what they're producing by way of a tailings product. They're just going to throw everything at you that they didn't want. So if someone leaves a hose water on, suddenly your feed dilution changes. If somebody changes the mineralogy without telling you, or the particle size. So we see changes in the product coming into thickeners, and we have to design thickeners for operating windows to actually adapt to that. And then the final aspect from a thickening perspective is the pumping. We're starting to see increasingly large, higher pressure, higher flow pumping systems coming into the market, which are addressing the needs that often historically were a restriction on what we could do. So you see some of the positive displacement pumps now are very, very large, and it means that we can get away with single unit pumps to actually produce or accommodate large capacities. So that's addressing one of those difficulties. And then I've tagged on the bottom there just a little note about in-pipe or end-of-pipe treatments. This is another aspect that's getting a lot more attention now, is perhaps we can thicken it partially and send it down the pipe because that maximizes or optimizes our transport costs. But then we can actually apply further applications of flocculants or chemical treatments to improve the way the material settles and separates from the water in the tailings facility. And I think there's a lot of work going on in red muds, for example, looking at exactly that to try and improve how we can separate the water from the solids once it's in the tailings facility. That allows us to minimize that retention time of ponds in the facility, and therefore minimize the amount of water we're storing. So looking now at filtration, final section from me. This is kind of like the family tree of filters. So we can go down the vacuum route where we've got discs, we've got horizontal belts, and we've got drums. Or we can go down the pressure filter route where we've got plate and frame, we can stack that vertically, or there's a sort of a compression thickener in the center there, or a belt press, sorry. If we're looking at surface disposal of filters, then we're principally looking at horizontal belt filters or plate and frame, depending on the deposition that we're going with. So this is going to give you a wetter cake, but it's a lower cost, or can be, not always, typically a lower cost solution than a plate and frame, but the plate and frame gives you the lower moisture content. So it depends what your drivers are as to where you're going. If we're looking at backfill, then we're still focused on either typically vacuum filtration, be that horizontal belts or discs. Tend not to use drums quite so much. But again, when we think about the fact that process plants or comminution circuits are getting finer, producing finer tailings, that's starting to knock some of these vacuum filtration options out. So we're being pushed down the pressure filtration route purely because of the material we're producing from the tailings dam. This is considerably more expensive than these, both in capital and sometimes in operating. So again, going back to what I said previously, there can be a trade-off between what we do in the process plant and the tailings we produce, based on what we subsequently have to do to manage those tailings. Some of the considerations we're looking at when we're thinking about filtration. So we're looking at what our moisture content needs to be at the end of the process. That depends on how we're transporting it. There's no point putting a fairly wet, high moisture content cake like this in the back of a truck. By the time you've driven it several kilometers, you'll have two products in the truck. One will be water, and one will be a solid segregated cake at the bottom. The water will come out, or has already come out all over the haul road. The cake won't come out the truck. So you need to think about these sort of things as to what you're trying to do with them. Also, when it comes to deposition, sometimes these are actually producing a cake which is too dry for the optimum deposition. So it can actually go too far the other way. So we're actually having to wet the solid, the material, before we actually place it. I don't know, Chris, if you're talking about that at all. But, capacity of the systems. So we're starting to get, these are starting to get to some really, really big units, which is helping to drive the operating costs. And I noticed there's a chap from Ethel Smith at the back there, and they've recently produced their I think it's called the Colossus pressure filter, which each of these frames, these plate frames that sit in here in this Colossus machine are 2 meters by 4 meters, so they're really quite vast. And increasing the capacity of these units is helping to drive down the cost of them as a whole, because we're actually getting economies of scale, and we'll have to increasingly do that. You can't have 20 or 30 of these lined up because they don't have the capacity. The costs just become prohibitive. Footprint. These are great if you've got loads of space, because they're pretty big. Some of these can be 20 to 30 meters long. These obviously give you a much smaller footprint. So if you're in outback Australia, where it doesn't rain very often and you don't need a roof and you don't need a shed over it, that's fab, because you've got no real restrictions on space. If you're in Kazakhstan and it's 45 below, you don't really want to be outside. So we're needing to put these things in buildings. And then finally, flexibility to change. No ore stays the same through the whole life of the project. It does change, it does adapt. So which of these units or which of the systems you design or select is more accommodating of change further down the line? So this is more sensitive to particle size than this, potentially. So again, it's just thinking about these things. Last couple of slides, just some of my thoughts on filtration. I put this up as a presentation I did before. The question is obviously something we should be doing. We should all be filtering our tailings. That's what we should be doing. It'll avoid the Mount Hollies, it'll avoid the Samarcos, it'll avoid all of that. First of all, we talk about dry disposal. It's not actually dry. It still has somewhere in the order of 10 to 15% moisture, which is still a fair amount of water, and it can still move, it can still flow. So first of all, it's not dry, it's just not as wet. Cost is still a major obstacle, okay? But we are starting to see that resolved, but not necessarily through engineering. Regulatory pressure is huge. So you look at BC in Canada, where they had the Mount Holly disaster. There's huge pressure to go with pressure filtration or dry stack tailings. It's the biggest motivator for it from that regulatory perspective. So that's pushing people. We're facing situations where clients are having to do it because they're demonstrating gold standard, not because it's the best solution for their operation from a technical perspective, but they're having to do it because that's what the authorities have demanded and expected, and that's going to increase. So you are going to see situations where the permitting authority says, I don't care what you do, I want one of those. So how do we make the costs fit? I think better appreciation of long-term liability costs, long-term closure costs, helps to provide the justification for the in-operation costs, the high capital, the high operating costs that we might face. We can justify those because we're minimizing the long-term liability costs. It's a difficult sell when you're producing for today, but it is there. Increasing system capacities, as I've said, that gives us the economies of scale, which is helping to drive down costs. A genuine objective to meet closure liabilities. I think we're starting to see operators and owners being a lot more genuine about the desire to meet long-term operating liabilities and responsibilities. And then finally, the need for a social license to mine. It's something that we'll start to see more of again, where there's so much regulatory NGO pressure that in order to get that social license, you have to demonstrate you're doing best practice, gold standard, etc. And whether that be the right answer, there'll be pressure to do it regardless. Filter tailings is not always the right answer in certain climates. How am I doing on time? Fine. Okay. If you've got a very wet climate, probably a filtered tailing stack is not what you want, because you're going to spend your whole time managing runoff and catching the material that's washed away rather than actually depositing the material. Equally, if you've got a very, very dry, very windy climate, you've got to manage dust propagation. So climate is an important aspect. So I've touched on some of those aspects there. So I don't think it's not the be all and the end all. Okay, it's not the only answer, but it is an answer, and there will be increasing pressure to meet that call. Right. Okay, final slide, just to summarize. So prevention is better than cure, and I think we need to be looking at technologies which allow us to reduce the amount of waste we produce in the first place. And I've talked about some of what those are. You know, better resource definition, mining less. If we've got to mine it, then how do we separate out the bit that we want from the bit we don't want? If we get the bit that we want, how do we maximize the recovery from in there? So that we actually get all of what we want out of that material. And then for what waste we do generate, let's make best use of our void resources. So if we've impacted the area already because we've got a pit or we've got void space underground, let's use that. It saves impacting somewhere else first. There will be motivation to engineer our waste. Okay, let's think about it as a product. Let's not just think about it as what's left. Think about it as a product and the cost benefit that comes from that. Co-disposal of coarse and fine material can offer benefits, and I think there's a lot of research going into that. It comes out, it doesn't come out as a coarse product and a fine product from the ground naturally. Nature co-mingles everything. That's what it does. So we need to be thinking about how we put it back in that area. And then for tailings disposal, we have to have a motivation for less water. That's absolutely clear, and there's no doubt about that. So yes, we should be looking at dry stack, but not always. Okay.
Thanks, Steve. Does anyone have any questions for him?
Ну, во-первых, во-первых, Стивен, большое спасибо за содержательный и очень полезный доклад. На самом деле мы много интересного слышали, и все это можно использовать на практике. Я думаю, что во время перерыва мы с вами должны будем побеседовать на эту тему. А во-вторых, я хотел бы сказать, что вы не сказали ни слова о самом радикальном способе снижения отходов. Это оставление всей горной массы, которую мы вынимаем на поверхность, оставление ее под землей. То есть применение технологии вычелачивания, или скважинное вычелачивание, или плотное вычелачивание. Над этим мы в Казахстане сейчас работаем, но я думаю, что это история долгая, но если весь мировой опыт учитывать, можно будет совместными усилиями достичь этих результатов положительных, наверное, не в короткий срок времени, ну исторически короткий срок времени. Вот. Я думаю, что это самый радикальный способ, правильно? Ну и во-вторых, По предобогащению вы говорили о том, что чтобы уменьшить количество отходов, складируемых в хвостохранилище, надо заниматься предобогащением. Действительно, в корпорации «Казахмыс» мы, в том числе я, серьезно еще занимались предобогащением в течение последних 4-5 лет. И сейчас мы запроектировали 4 объекта, на которых будет производиться предобогащение с применением рентгеново-биометрической сепарации. Строительство начнется в мае месяце в этом году. Я думаю, что до конца этого года будет 2 объекта построены, в 2019 году еще 2 объекта, ну и впереди у нас еще 11 проектов таких. Мы 27-30% породы будем отсекать до отправления на переработку на фабрику. Таким образом, естественно, на такое же количество мы снизим отходы, которые будем отправлять на хвостохранилище. Вы об этом уже сказали, так что это мировая тенденция, наверняка мы к этому идем, и все будем приходить в зависимости от того, насколько это эффективно и насколько это экономично. Ну и третье, по пастовому сгущению хвостов. Ну, технология использования пастовых хвостов, или так называемая, в Казахстане она была названа тиксотропной закладкой, она начала использоваться с 1980 года для того, чтобы обеспечить твердую закладку в шахте. Почему мы пришли к мнению о пастовой закладке? Потому что хвосты, подаваемые для закладки в смеси с цементом, в том количестве, по той технологии, которая существовала, она вынуждает огромное загрязнение, приводит к огромному загрязнению подземных выработок, потому что вода вытекает со всех этих из камер, которые мы закладываем. И мы пришли к мнению, что надо создавать пастовую закладку, это была тяжелая работа, мы ее создали. Ну, сейчас это во всем мире используется, но впервые это было в Казахстане в 1980 году. Вот. Поэтому я думаю, что это тоже один из способов, если стоимость хвостохранилища, транспортирование на хвостохранилище, укладка, контроль за состоянием хвостов будет стоить дороже, чем сама закладка. Почему на закладку люди не идут? Потому что добыча системы с применением систем разработки закладки это гораздо дороже, чем добыча с обрушением или с открытым выработанным пространством. То есть здесь надо находить экономический баланс, экономическое равновесие. Ну, я немножко дополнил ваш доклад, я извиняюсь. Спасибо большое.
No, that's absolutely fine. I think it's great. I mean, it's nice to hear that you're already doing so many of the things that I'm talking about, and it's certainly not. It's not to suggest that I don't think you will be doing that. It's more a case that we don't know that you're doing it. But it's great to hear that you're doing the pre-concentration. I think that's a huge step forward, and I think, as you say, it will become increasingly important across the whole world. And then that balance, you're absolutely right, the cost benefit of whether we put tailings on surface or underground. I think there will increasingly be motivation, not just from a production perspective to put tailings underground, but from a social, environmental perspective, and that will drive the acceptance of the cost, because sometimes we have to do things even though it's more expensive. But I think you're right, and looking at that balance between what goes on surface and underground is important, for sure. So thank you.
Okay, well, if there's no further questions, we'll get on with Chris's talk, and he's going to talk in more detail about tailings. And if there's any questions at the end, you can ask them now. So please take it away, Chris. Thanks, Steve.
Hello, my name is CZAJEWSKI. I'm a tailings engineer for.
Press the mic. Talk at the top.
The microphone.
Oh, okay.
Look at the red dot. Focus on the red dot.
I'm a tailings engineer working for SRK, and topic of my presentation is basically safety of a tailings facilities. It doesn't really matter which facilities we're talking about, whether that's traditional facility or a paste facility or dry stacking facilities. They all carry some significant risks. I've spent about 20 years working in North America on the operating facilities, as well as about 10 years here, more than 10 years working in Russia and Kazakhstan and Europe and so on. So I've got a little bit of your perspective, how you design and how you manage the facility and how you manage the risk. So I encourage you, please ask the questions during my presentation. So I think I still have an hour to go, so there's plenty of time to ask questions.
You can't be close to the mic.
Okay. Okay. Basically, our work in Europe is based on the we use as a reference the best available technique, and now recently we have published the sort of European guidelines. This is basically a little bit of interpretation of best available techniques. And when we were developing those guidelines, we were contacting our friends in North America, in Canada, as well as in Australia. So hopefully this document could be useful. Just to give you a little bit of the background on the tailings facilities, this is sort of general public. Some of you don't have maybe haven't came across the tailings facility, but basically the tailings facilities could range from the just the typical facilities, which are here. This is and basically this is slurry facility where we dispose the slurry. This is the containment dam. And this is basically deposition taking place from the beach, from that containment here. And as you see here, this is the proper way to deposit the tailings, where you have a huge dry beach above water, and this is not a good way to deposit. This is just on one slide how to deposit the tailings, where you have the water just coming up to the containment facility. Okay. The tailings facilities tend to be not that expensive because we're relying on the tailings being against the containment. Okay. If we were to build a safe facility that has the water against the dam, the cost of the facility would be order of magnitude higher. So this is very important to remember. When you operating those facilities, make sure you always have a beach above water against your containment. So this is traditional facility, and this is dry stack facility that Steve was talking about. A nice thing about dry stack is that you don't have to build the containment almost. All you have to do, you may have to only line the dry stack and stuff, but obviously there are costs with the dry stack that Steve was talking about, and I will talk about that later. So this is again just going over different types of facilities. So this is the we subdivide it into external facility and internal facility. internal facilities, you could store it above the ground, under the ground, sorry, or in a mined-out pit. Okay. And for example, when I was working for oil sands in Canada, we would build the external facility, which is those types, for first 5 years, 5-10 years, and then we would put all the tailings in pit. Okay, and this is very good way of doing it. I know there is a problem with the geochemistry that Carl was talking about, but from the physical stability, this is really good way of doing it. Okay, and there are external facilities that are 99% of your facilities here in Kazakhstan, and you like to go with upstream construction, so it's called namivnym sposobom, da? Because this is the most economic way to do it. There are other facilities such as downstream facilities. Nalivnym sposobom means that you have to build the whole facility in a downstream direction, and that is quite expensive. That's why most of your tailings are namivnym sposobom, the upstream facilities. Okay. And just to concentrate on your upstream facilities here, I just put up this slide, and this is something to think about. Lots of, when we're talking about upstream facilities again, probably 80% of your facilities are upstream. So you go for the cheapest solution here, okay? And this is where your biggest risk lies, okay? And I will be talking about how we can mitigate that risk with those upstream facilities, because that is the biggest exposure here, okay? So first of all, it's been assumed that you can build the upstream facilities only for the tailings deposits that are segregating, and they have about 40 to 50% sand. You have to really, when you go in an upstream direction, and maybe I can go a few slides, this is the upstream namivnym sposobom. When you step on consecutive tailings layers here, we assume that this is a pretty strong beach, and we can step on it, and it's not going to liquefy for us. Okay. So we assume that we can use only this method when we have 40 to 50% sand. Okay, so more than 70 microns. Okay, or something like that. If you have slimes and you're using this method, it's quite risky, okay? So going back, the discharge requirement, this is sort of the same requirements for all the facilities. And the operators like to use the tailings facilities for water storage. And this upstream facility is not suitable for water storage, really, okay? So if you're planning to have lots of water inventory in your tailings facility, you probably have to look at some other facilities, such as central line facility or downstream facility, okay? As well as if you are in a seismic region, you should not really use the upstream facility unless you know that the sand has been deposited or you had very good beach above water that you can step for the upstream facility na myrnym sposobem. Another sort of very good criteria is that if you plan to raise your facility really fast, you shouldn't be using the upstream construction as well. Upstream constructions are really good only for 4.5 to 9 meter sort of rate of rise per annum. Okay, if you're raising, let's say, 20 meters or 30 meters, don't use this method. Okay. And this is, I just wanted to talk about the cost. Obviously, the upstream construction is the cheapest, whereas the central line and the downstream construction, it is the most expensive, and obviously that's why 80 or 90% of all the structures go upstream construction. Na mywnym sposobem. And here on this slide, a little bit talking about the again the deposits, different deposit methods. This is the external deposit method. So when we build the standard slurry disposal, at first we build the containment dams here, and then we'll just fill the tailings. When we put the paste or thickened tails, we reduce the requirements for the containment dams because we can maintain the slope here if there is a central disposal. But we still have the risk of the failure of this facility. So by going to paste, you probably have a better water management, as Steve was telling, but you're still risking a failure here, okay? So it's better to have a well-built slurry disposal than poorly built the paste disposal, okay? And you have to keep in mind that the failures are still possible in a thickened tailings or a paste disposal, okay? If you go to dry stacking, obviously you don't have to build any containment here or very little containment. I've seen lots of construction still with dry stacking where they have a rock containment. Even so, it's not necessary to do it, yeah. But people like to have a rock here on a surface because of erosion. It's very important to remember also with dry stacking that you need a clarification pond still. Why you need a clarification pond? Because when you have a storm events here and your storm water is running on your dry stack, you still need to collect that water and put it in the clarification pond as well. Okay, so we talked about the upstream construction, downstream construction, the most expensive, and a central line construction. And we talked about the valley disposal. That's what you still have lots here. Even so, the most popular in Kazakhstan is sort of paddock disposal, where you on the flat ground, you're just building the all around tailings facilities and so on. So it's nothing new. I just wanted to show this slide for people who are not involved day to day with the tailings. This is basically a mill. We send the slurry here to the this is the tailings facility. This is the containment dam. And this is the clarification pond. And we disposing the tailings into the facility here. And we just, I just put it here, the reclaim pump, pływająca stacja. Most of the time here in Kazakhstan, you have the decant tower, which is basically to take the water from the tailings here. You put a vertical section here, and then you put the pipe through your containment dam here. This is something that is done throughout like Russia and Kazakhstan as the most popular method. Just wanted to bring to your attention that, for example, in North America and in South America, we would use the reclaim pumps because of the safety. Solution with the decant tower in Russian is called kovodets. It's that very often we have a failure underneath of this containment dam. Okay, so it is quite risky, and I just wanted to bring your attention and suggest that you use more of the pływająca stacja. Okay. The next thing I'm going to talk about is the recent failures and how you analyze the tailings of the tailings facility and the different codes which were already discussed before. Okay, I'm not sure, are there any designers of a tailings facility here? Like engineers that were designing tailings facilities, or like in the room? Are there any engineers that designing tailings facilities? Строители есть, да, но не. Okay. I just wanted to bring the differences, because there were the earlier question, what are the major differences between the SNIP or GHOST standards, Russian standards or Kazakh standards, and international standards? And the biggest difference is in the factors of safety we're using. Somebody said that the designers here in Kazakhstan and Russia are more conservative. Actually, it's other way around. It's we designed to factor safety 1.5, and the designers here in Kazakhstan and Russia are designing to 1.14 or slightly higher, depending on the class of the structure. So this is the biggest difference. The second biggest difference in a design is how we test the tailings and how we test the samples and so on, like a clay samples, like there is no difference in testing the sand samples, but there's a huge difference in testing the silt and clay samples, okay? And we coming up, because of our different protocols, we coming up with entirely different techniques, entirely different strengths. Another difference is that we using the both the effective stress analysis and the undrained strength analysis. And the institutes, the practitioners here, are using only effective stress analysis. Okay, and this has a major implication for the safety. So at first, I thought I'm going to show you a couple examples of the recent failures. By recent meaning last 20 years or something like that, that have been documented, and I started just to show you that those failures have been recorded since the beginning of 20th century, and basically with the most of the failures happening in 60s, 70s and 80s, and it's a decreasing trend for the failures. Now, those are reported failures. Lots of failures are not reported, and especially in the countries where you know they have different reporting sort of requirements and so on. So we're all learning from this, from those failures, and I'm going to be discussing later on, like for example, SRK failure or Mount Cooley failure. Even so, it doesn't reflect very well on operators. They are willing to share their experiences. As Steve said, rather than firing the guy for because he had a failure, there is the tendency to keep that guy because he has experience now and hopefully will not repeat that again. So those failures, I subdivided into a few categories. This is the failure, like a foundation failure. This is failures usually on the clay layer. And again, I just wanted to bring this, when you testing using the SNP protocols, most of your labs are very well equipped here in Kazakhstan. However, they're using different protocols, and it takes long time for the technicians to test properly. This has to do with the saturation of the samples, and then slow enough testing, so we get effective stress parameters. The next reason why we have failures is lots of karstic formations. I don't know whether you came across here the karstification. And another way, another reason is the liquefaction. Okay. Liquefaction failures are becoming, the design for liquefaction becoming the biggest trend recently. Okay. Another reason for failures is the bad water management. Okay. And bad water management is actually underlying cause of the most of the failures that occurring in the world. The bad water management draws very, chain reaction. First of all, if the chemistry of water is not recognized, you have a problem with clarification of the water, that therefore you have to keep high water inventory. Then, when you have to have high water inventory, then your water is coming very close to your containment. This creates two problems. First problem is it's very dangerous because that water is sitting now very close to your dam. And the second thing is when you dispose the tailings, it creates very very low density now material. And now if you're building upstream, you have to step on that very low density material. So that creates the problem for your liquefaction failure. So you basically, this problem leads to other problems here. And here are the ecological failures, and I just listed if you have a water contamination, even so you haven't broke or breached the dam, but you have lots of groundwater contamination, that is considered to be a failure as well, because you haven't really contained that material physically or geochemically well. And here I just pick some up from KRIS research. What are the main causes of the failures? Let's say in end of last century versus now. And you can see there is a trend. The KRIS research really said the weather causes most of the failures. Well, all the facilities have to be designed to cope with the weather. So whatever weather problems you have, it has to be incorporated. Okay. The next cause is the management. Okay. And this is mostly basically most of this is the water management, as I was talking. Fairly small is the subsidence, and the slope instability is listed only like a 10%. But believe me, most of the failures are caused like a slope instability is the problem, yeah? And overtopping, which obviously relates to weather and some seepage and structural defects and so on, okay? So you can see where people classifying this as a causes of the failure. Okay, and how much failure costs? Well, I just put it few numbers. Typically, to fix the tailings facility, it costs anywhere between $30 to $100 million. But ecological cost, for example, Samarco, I just picked it up from the literature here, is $5.1 billion. It cost them that failure. Okay.
So that's the one in Brazil?
Yeah. So those are very, very big costs. So I mean, we all go into upstream construction, namivnym sposobom, because this is the cheapest, but you always have to think, if something goes wrong, what it will cost. Because even your very low categories structure, let's say 10-meter high structure, if it fails, what would happen? Okay, is that going to shut down your operation? Is that fixable? What is it? It is a big cost, and I've been involved in a few investigations after failure, and it's not very. You cannot put those costs very well, but you don't want to get into that situation. So, so the most So the most important things for the tailings management, it's a water balance. Get a water balance right and spend lots of time analyzing this, making sure you don't have too much water in your facility, and if you have lots of water in your facility, make sure you're building very good containment. And building very good containment could be quite expensive. But if you know you're going to have lots of water, make sure you build a good containment. The next thing is the operations. You have this, I notice here in Kazakhstan, really good operation. You're very diligent in terms of the getting the everything recorded, and sometimes you do every shift or twice a shift, and so it is fine. Look at your design limits. Very often, original design tells that you have to have a certain beach above water, let's say 100 or 200 meter above water, a beach above water. Stick to it. And if you transgress, your water transgresses to your containment dam, just make sure you inform your designer and tell them to deal with that, okay? He would have to decide it. As I said, you document quite well. What I have noticed here, very often you produce your initial design, let's say a few years ago, and you just follow that design without any changes, okay? What I found it like a big difference in Canada, we were changing design every year, or sometimes twice a year, okay? And this has because of two causes. First, once you start building your tailings facilities, the condition changed. You're getting different strengths, different water levels, piezometric levels, different materials. Secondly, sometimes you're getting everything as designed, but because it's so expensive, that operator wants to change for a cheaper design. So once you know how the materials are performing and your tailings facility is performing, you can probably optimize your design and change into the cheaper design. Okay, and those are the next thing I wanted to show are the previous failures, and I started with Marius Prut. Jane already mentioned that in her presentation. That was in South Africa in 1994. I picked this because this has been designed by good engineers with a big factor of safety. Okay, the factor of safety on this one is 1.7, so it's much bigger than 1.14 that you have in your. And this thing failed, and this is failed in a static liquefaction. So it wasn't a seismicity. The water was quite far away. Everybody thought that the dam was extremely safe, but it turns out that it failed really, really fast. Static liquefaction, and it's quite well documented. What had happened basically, people just heard a big like a big thunder, because it failed very loud. Okay, you could hear that about 5 kilometers, from 5 kilometer distance when it was failing. And basically, this is the failure that I think about 20 people died during, and it covered the whole village with the tailings and so on. But this is sort of the one of the first incidents that people start thinking about static liquefaction. Static liquefaction is really a mode of failure when you have very loose material, basically trying to contract. Okay, so very loose material becoming all suddenly contractive, and the tailings or dam becomes basically a fluid. Okay, so this is the liquefaction, and this is what had occurred here. Another big you've all heard is Mount Pulley. Again, why I'm showing those failures is because those were very well-known operators, and they've been designed by very good engineers, and they still couldn't manage to basically it's about 20 million cubic meters of the tailings has been released to the one of the nicest and cleanest parts of the world. Okay. The basic problem here was very weak clay layer at the bottom that hasn't been tested properly, and this is in Canada. So they had the best operators, best designers, best reviewers, and they still got that problem. The one that I wanted to focus a bit was Samarco, a 2015 failure. Okay, and again, a very good designer. Rio Tinto is the operator, so they really cognizant of the best practices and everything, and they had a typical liquefaction failure. So this is just a map, and this is pre-failure, and I will talk about that. Basically, this is the valley type of tailings facility, and you just notice here they were building here with a nice slope, and then they notice it would be better seen on a cross section that they have a problem here with the drainage of the material. So they decided to move this tailings, sort of flatten the slope at the left abutment. Okay, but that wasn't enough for them to prevent the failure. So they did, and I'm gonna okay. So basically, the failure happened in 2015. 12 people died. Then there was a big investigation. That's why we can all talk about that. So this is another example how you can learn from the old mistakes before and after. Okay. So this is basically talking about how it was. What I wanted to show, I'm not sure I have enough. How is that?
About 10 minutes. 10 minutes.
Still left? Okay, so I better remove. Okay. to show you the cross section of that tailings dam. Okay. It was well designed dam. It started from a starter dam here, and then they basically deposited sand on it. They used a cyclone. So they deposited sand here, and they deposited sand here, and they had a 200-meter beach, etc., etc. So the other cross section is basically showing this is very well built structure. Okay. So this is sort of intermediate. This is about 2012 cross section, where, as you see here, you have the upstream construction, nice sand here. However, they got some slimes. Slimes are the fine material, fine clay material. And why did they got the slimes? Probably because they had a water line just coming really close here. And you get those slimes anytime that water comes very close to you, and you basically now deposited your tailings in under the water into low energy environment, okay? And then you're getting those slimes here, okay? So what they decided to do, because in addition they were getting the failure of the gallery, like a seepage gallery. So the water table, instead of just going like this here, it actually did not want to dissipate, and some of the seepage was coming here on the slope. Okay, so in their wisdom, they decided to flatten the slopes and move this a few hundred meters and basically build far away. So so this is where liquefaction has occurred. Just a moment. Okay. Sorry. I still have 5 minutes. 5 minutes. Okay. So I will. So the basic. Sorry. The basic conclusion here. Just make sure you don't build on a loose deposit when you're going upstream. Okay. Okay, the next slide I wanted to show, which in my opinion is a proper way of designing those structures. First of all, what we do in here, especially like in Russia, we design our tailings facility based on effective stress analysis, and we take under consideration only design, the design for erratic surface. Okay. What we don't do enough here is the consolidation of the tailings. When we're going upstream, we don't consider in our analysis how fast those tailings will consolidate, and very often we step on unconsolidated tailings. But the most important, what I wanted to focus is the liquefaction failures, and those occurring quite often, even so people don't report them. So, as I was telling before, is basically we need to start testing the tailings for undrained undrained mode, as well as the analysis. We have to do both the drained and undrained mode. And why do we do this? Because we just want to make sure, and this is taken from the paper by McRoberts in '99. This is basically, he just shows for the upstream construction what is the proper way of building the upstream. So he considers, and this is what the paper proposes, basically when we're building the upstream construction, make sure you have very wide beach above water here, and you only raise your facility here on the on very well strong material. Okay. Make sure, like in a case of Samarco, you don't have any fine material, slimes, in this zone here. If you have slimes in this zone here, you could be prone to the similar failure as for example, Samarco had. Okay. Likewise, other way around is when you, and this is where we see very often, you don't have very wide beach and your water just against your containment. So this is no good. Okay. So I just thought I'm going to show you the one of the tables from the Canadian Dam Safety Association about factor safety. Basically, what they consider that at the end of construction, before the filling of the tailings, you need a factor safety 1.3, and after you start filling it, you need a factor safety 1.5. So those are much higher factor safety that you're using here in Kazakhstan. And there is a reason for it, because the in the codes that you're using, you just basically mimic those codes on the structural engineering codes, okay, structural and civil engineering codes. And structural engineering codes go to very low factors of safety. In terms of the soils and rock, the strength of material is very uncertain. It's not like steel or concrete. Like, you know that steel is 300 MPa and it's plus minus a bit, okay? You know that concrete is 25 MPa, whatever you order, okay? In terms of the soil, you normally can determine the strength of soil with very high uncertainty, okay? So the probability that your clay is 25% or 15% is very high, okay? That's why you're using the very high factors of safety, okay? And this is something worth to remember. Are there any questions? Yes.
Так, ну попробую громко сказать. Вот инцидентов, которые были показаны, они были все для намывных хвостохранилищ. То есть, если бы конструкция была другая, исключить, ну, если бы были наливные хвостохранилища, этих бы аварий не случилось, скорее всего, или нет? Так нельзя говорить однозначно.
Well, if we yes, the failure would not occur unless there was some problem still in the foundation, like in a clay foundation, okay? But generally those failures that I was showing, they're relating to liquefaction. Either it's a static liquefaction or the seismic liquefaction, okay? And this is something that this hasn't been studied for a very long time. The present method to determine whether your structure is liquefiable or not is to go with the cone penetration testing. This is basically statyczyjskie zondirowanie. We call this statyczyjskie zondirowanie. Basically what it is it has a cone that progresses with a constant speed down, and it will determine whether you are prone to that liquefaction or not. Okay. Because well-built dams doesn't matter how fast you build them, how much seismicity you got, whether you got lots of water or not. Well-built dams will not fail. They're designed to hold the water. If you have loosely built dams, or in an upstream direction where you're stepping on your very loose materials, anything can trigger it. Okay, and this is worthwhile to tell it. Another very important thing is, when you have those liquefaction failures, basically you cannot monitor with anything. Like you cannot put the a piezometer and monitor, or you cannot put the survey point and monitor. They will happen really fast. They will happen instantly. They would just go. Okay. So those type of failures are becoming more and more problem. Yeah. And this was Samarco failure and so on.